Right, we are on our way towards the Wheeler equation. So it's about perturbations of the Schwarzschild metric. So our metric is a Schwarzschild metric plus a perturbation. And we have seen that for odd perturbations, odd with respect to parity transformations, the h mu nu after an appropriate gauge transformation can be brought to the following form, that instead of the 10 components which we have in general, we have actually only two functions, two coefficients functions, which I denoted VALM, the index A tangent values R and T. And the basis vectors which are related to this, I think it was a phi or the psi? Yes, a phi. LM sigma. Sigma takes values theta and phi. So these are the, the coordinates which are fixed on the sphere, and these are the coordinates which parameterize the sphere. Dx A dx sigma. And we have done this for fixed LM. Yeah, LM are the, the quantum numbers which label the spherical harmonics, which we have used for our basis. And here I forgot something to say last time, which is not quite unimportant. I forgot to say that everything I'm doing here is true only for L bigger or equal than 2. So two cases are excluded. The case L equals 0, that's a monopole perturbation, is excluded. And the case L equal 1 is excluded, which is a dipole perturbation. Well, actually, you can easily, for the monopole term, you can easily see that what I've done doesn't work. Why not? Because this was, one of the basis elements was a gradient of the spherical harmonics, if you remember correctly. And the other one was constructed orthogonal to this. But if L is equal 0, then you have only y 0, 0, and this is a constant. The gradient of a constant can, of course, not be used as a basis element, yeah, obviously. So what I've done does not work for L equals 0. And if you look more carefully, in particular, if you look at what we have done with the gauge transformation, you will see that it also doesn't work for L equal 1. So these two cases have to be excluded. I forgot to say this last time. Actually, you can treat these two cases separately. But, actually it should be fairly clear without calculation what the case L equals 0 and the case L equal 1 is about. Remember that when we considered perturbations of the flat background, we found the result that the leading order term for the radiation field is a quadrupole term. Yeah, so the monopole term and the dipole term give no contribution to the radiation field. What's the monopole term doing? The monopole term is just, it's spherically symmetric perturbation. So in the case of a spherically symmetric background as Schwarzschild, and the perturbation which is also spherically symmetric and satisfies the vacuum field equation, the only thing that can happen is that the mass is changing. Yeah, the mass becomes bigger or smaller. By the Jepsen-Birkhoff theorem, there's a unique solution for this situation. Spherically symmetric vacuum means it must be Schwarzschild. Schwarzschild has one parameter. If you perturb the Schwarzschild matrix, then the only thing you can perturb is this parameter, the mass, or the Schwarzschild radius. So you just get a variation in the for the L equals 0 term of the mass of the monopole term, and this of course has nothing to do with radiation. Yeah, it doesn't radiate. There's no gravitational radiation associated with this. The case L equal 1 is a little bit more complicated. But also in this case, you can show that it's not associated with radiation. So it's exactly analogous to what we have done on flat space-time. So in this case, what happens is this dipole perturbation does two things. It shifts the origin. This produces a dipole term, and it produces a rotation of the black hole. Yeah? So what you get is a Kerr metric in linear approximation. Yeah? So you linearize with respect to the spin of the black hole, because if you linearize everything with respect to these things, you don't get the full Kerr metric. You only get it linearized with respect to the spin parameter. And the Kerr metric also is not radiating. It's a stationary metric. Yeah? So it has nothing to do with gravitational radiation. So also In the case that Schwarzschild is a background, you have the statement remains true that in lowest order, the radiation is given by a quadrupole term. Yeah, it starts with a quadrupole term. And what I wanted to discuss here is actually only everything beginning with a quadrupole term. So I didn't want to consider the L equals 0 and L equal 1 term. I just forgot to mention this. And actually what I've written, the sums for the expansions, they begin with L equals 0 in what I've written last week, and this is wrong. Yeah, they begin with L equal 2. So I have to correct this. Okay, but for L bigger or equal than 2, it is true what I said. These things really are basis elements. So for all the perturbations, before we restrict it to the odd ones, what I've written down gives a basis for the scalar, the covector, and the tensor part. And they really are linearly independent. You can check this. Okay, now we have restricted to the odd perturbations, and we have to plug this into the field equation. So I did this last time. I wrote down the components of the field equation. There were 3 independent equations. The equations which I've written down were correct, but then I produced a mess when I tried to reduce this to a single differential equation for one variable. So I hope that I managed to do it today. So let me try this again. So insert into field equation. So you get, because of the symmetry, you don't get 10 equations, you only get 3. The first one I don't write down because we will actually not need it. I called it F1 last time. I wrote it down last time. But the other 2 I will need, and I have to write down again. So F2 is 0 is minus. So it's a system of differential equation for these coefficients, right? Where A takes the values R and T. dt, dr, dtlm minus dt squared, drlm minus 2 over r dt by tlm. Everything divided by c squared 1 minus rs over r plus 1 over r squared L plus 1 minus 2 VRLM. Oops. So that's F2. And the last one is a bit shorter. The last one is dr 1 minus rs over r VRLM minus dt VTLM over c squared 1 minus rs over r. So that's F3. So you see it's a coupled system of differential equation as you expect with Einstein's field equation for the 2 unknown functions which are left, VTLM and VRLM. But I claim that I can decouple them. I claimed this already last time. I hope today I can prove it. So I introduce a new quantity which I call capital QLM, which substitutes for the VRLM. It is 1 minus r, 1 minus rs over r, VRLM over r. Okay, so you see that this is very convenient for this expression here. So then we get, no, let me write it this way. F3 implies the following equation. If I insert this here for VRLM, then I get, yes, I guess what? So I get dr here, this term, 1 minus rs over r VRLM. This is this here up to the factor r, so I get rqlm. And the other one I think I just copy over c squared 1 minus rs over r is 0. So I can solve this for dt VTLM. So this is then c squared 1 minus rs over r, and I think I multiply this out. Yes. So I really, I calculate this with the product rule. So this is, if I differentiate the r, then I get a QLM. And if I leave the r and differentiate this here, then I get r dr QLM. Okay, that's it. And that's what I call F3 prime. So it gives me the first t derivative in terms of my newly introduced variable QLM. Here I have in F2, I have the first derivative, and I also have the second derivative, the mixed derivative, yeah, dt with the dr. So I also have to get rid of this term. So I get it if I differentiate this equation, which I've just derived with respect to r. Then I get this term. So differentiate with respect to r, then I get dr dt VTLM. Now I have to see how I combine this in a clever way. So let me see. Where am I? I have to find the right line. Here. S over r squared QLM. Yes, so I differentiate this term here. So I get these minus gives plus QLM. Then I get plus c squared 1 minus rsr dr QLM. And the same term I get if I differentiate this with respect to this r. So I get it twice. And then I get the rest where I leave the r invariant and have everything else under the derivative. C squared 1 minus rs over r dr QLM. Okay, and I call this F3 double prime. So now I have the two terms which are inconvenient in F2. I have expressed them in terms of my new variable QLM. So substitute this F3 1 prime and F3 double prime into F2. And then let's keep fingers crossed that I get the equations I want to get. So where is F2? Here's F2. So I have 0 is minus this mixed derivative, which I've just calculated. So this is minus c squared rs over r squared QLM. Oh, there's a minus. Minus 2c squared 1 minus rs over r dr QLM minus r dr c squared 1 minus rs r dr QLM. Okay, that's the first term. Then the second term, VRLM. VRLM is this here, so I have to substitute this. So I get minus times minus gives plus d2 squared. And under the derivative, I have VRLM. That's RQLM divided by this term. RQLM divided by 1 minus rs over r. And the last term, minus times minus gives plus 2 over r, and then the first derivative, which I have in F3 prime. Plus 2 over r, this term here. C squared 1 minus rs over r QLM. There was a plus 2 over r, then this goes away, so it's 2c squared 1 minus rs over r dr QLM. And everything is on top of c squared 1 minus rs over r. Okay, and the rest, where am I here? The rest I just copy up to the fact that I introduce for VRLM my QLM. So this is R QLM divided by 1 minus RS over R. So I have a 0 on the other side, so I can multiply everything with these terms. And another term should cancel. Let me see, hopefully this one. Yes, yes, you see. This cancels with this here. Well, this makes things already a bit better. So I have divide all this by c squared. So I get 0 is minus RS over R squared QLM. Then this here, there's a c square, this cancels. So it's minus R d by dr. 1 minus RS over R d by dr QLM. And here 1 over c squared. The time derivative acts only on the QLM. Yeah, these terms do not involve t. So I can write plus R over 1 minus RS by R. And then, no, here I am. And then I get 1 over c squared, second derivative of QLM. Okay, this was this one. And this is the last one, plus 2 over R. 1 minus RS over R QLM. And then the last one, which I just copied, plus 1 over R squared. There's an R here, an R squared here, so I get 1 over R. 1 minus RS over, no, nonsense. Oops. L times L plus 1 minus 2 QLM. Okay, what next? This is not nice. This in the denominator, so I multiply everything with 1 minus RS divided by R. And I think I divide by R in order to get rid of this term here. Yes. So I multiply with 1 over R, 1 minus RS over R. So then I get minus 1 over R means RS over R. QLM, this is divided out, so I get a factor 1 minus RS over R, dr. Yeah?
Shouldn't it be R to the cube in the denominator, not just R?
Oh, yes, you're right. Thank you. Yes, of course, yeah. Here it goes away. So this term goes away. So I have just 1 over c squared second time derivative, QLM, which is nice. And here I have plus 2 over R squared, 1 minus RS R squared, QLM. And here I get 1 over R squared, 1 minus RS over R, plus 1 minus 2 QLM. Let me see. Yes. Okay, I have to multiply this out. I have to combine these two terms. Let me see, where are derivatives? Let's collect first all terms with derivatives. Here I have R derivatives. Let me begin with this term. 1 minus RS over R, dr 1 minus RS over R, dr QLM. Here I have a T derivative. Let's take this term next. And everything else is proportional to QLM. Can I take something else out of the bracket? I think I can take a 1 over R squared, 1 minus RS over R out of the bracket. So then I get what? I get minus rs over r plus rs squared over r squared. This was this here. And this here plus 2 times 1 minus rs over r. And here I have plus L plus 1 minus 2 QLM. Okay, you see plus 2 minus 2. And this gives minus 2 rs over r minus 1. So I get this minus 3. Okay? Okay, that's almost, well, in essence, this is already the time-dependent Regge-Wheeler equation. One usually writes it in a nicer form. Here you have the r derivative always multiplied with a factor, 1 minus rs divided by r. So you can introduce a transformed r coordinate so that this becomes a derivative with respect to these new coordinates. And I think most of you have seen this coordinate before. Actually, it was introduced in this context by Regge and Wheeler. It is a famous tortoise coordinate, which is introduced in this way. It was introduced by Regge and Wheeler in this paper. And how is it defined? So then this term becomes nicer. This is the only modification we need. I explain in a minute why it is called tortoise coordinate. It's usually denoted r star, and it is defined as, let me see, where am I? Should have written it up somewhere. Ah, here it is. Very good. It is r plus rs log of r divided by rs minus 1. So r runs we are outside of the horizon of the black hole, so r runs from rs to infinity. Yeah. So let's see, what is the tortoise coordinate doing is if r goes to infinity, and this is infinity, and the log of infinity is also infinity. So r equal infinity corresponds to r star equal infinity. Yeah, so what's far away from the black hole is the same in the r and in the r star coordinate. But if the horizon is approached, if r goes to rs, then this is something finite. But r over rs goes to 1. 1 minus 1 is 0. The log of 0 is minus infinity. Yeah? So if the horizon is approached, then this term, this is finite, and this goes to minus infinity. So the tortoise coordinate goes to minus infinity. So what it does is it extends the interval from the horizon to infinity to the entire real axis, from minus infinity to plus infinity. So it shifts the horizon to minus infinity. And that's why John Wheeler called it a tortoise coordinate. It reminds of the, this paradox, Zeno's paradox of Achilles performing a race with a tortoise. So the tortoise has a certain head start, and as the paradox goes, Achilles will never reach it. Yeah, because when he has arrived at the point where the tortoise has been a minute ago, then the tortoise has already moved away, and this goes infinitely often. Of course, what Zeno was doing was just that he divides this finite interval into an infinite number of subintervals. And he erroneously concluded that this must be infinite. But you can have an infinite series which gives a finite value, of course. That's what happens here. So actually Achilles would win the race, yeah, to be sure. Anyway, so here, what's the analogy? The analogy is that here's a horizon is shifted to infinity. So you never reach it in these coordinates. Yeah? That's why Wheeler calls this a tortoise coordinate. Okay, if we differentiate this, then we get dr star is what? Dr star is dr plus rs divided by r over rs minus 1. And the inner derivative gives the 1 over rs times dr. And if I write everything on a common denominator, r over rs minus 1, then I have here r over rs minus 1. This goes away, of course, plus 1 dr. So this is, if I multiply with Rs over R, then it is dr over 1 minus Rs over R. And this means that if I take the inverse, that the derivative with respect to, the t coordinate is not affected. Yeah, it's just the transformation of the radial coordinate. T remains t. So the partial derivative with respect to R star is related to a partial derivative with respect to R. I just have to take the inverse of this here. So this is 1 minus Rs over R dr, and that's exactly the expression which we have here. Yeah? So this is the derivative with respect to the tortoise coordinate. That's how it was introduced. And then we get what is called the time-dependent Red-Wheeler equation. So this is 0. Now it's the second derivative with respect to the tortoise coordinate of QLM. So QLM is a function of t and r. And r I can express in terms of r star with the help of this transformation. This transformation can be solved for r star. It cannot be solved for r because it is, it's a transcendental expression, right? The r occurs once here as a r directly and once under a log. This cannot be solved, such a term, yeah? So it's what is called a transcendental function, but nonetheless there is a unique inverse function, yeah? So r is given implicitly by this expression as a function of r star. And if I substitute this, then I get QLM as a function of r star and t. And that's how we want to look at it. dr star QLM with a minus sign, right? So with a minus sign in front of everything. And then I have plus the time derivative with a c squared for dimensional reasons. And then I have something which I call VL of r star. And that's the QLM with VL of r star. I give it as a function of r, but there's a unique bijective relation between r and r star, so I give it implicitly as a function of r star, and it's exactly this expression here. Yeah, everything which is left, 1 over r squared, 1 minus Rs over r, L plus 1 minus 2. That's it. No, the minus 2 is gone. There's instead, wait a minute, there's something else. What have I done here? Wait a minute, this term is not good. Why do I get this term? I only want to have this here. Minus 3 Rs over R, that's it. Why do I get this stupid term here? Where is this coming from? I don't want it. 1 minus R squared. What have I done here? Let me see. It comes from this here, right? Do I get this term another time? Let's see.
The powers are correct there.
Here's something with this term, right?
If this coming from the first term, then I guess there's something wrong there.
So let me see. I just copied this. I think there cannot have happened anything with this term. This is also correct. And then comes this here. So I take 1 over r squared out of the bracket, 1 minus Rs over r. So I get minus Rs over r. Minus this term is just nonsense. Yeah, I have taken this out of the bracket. So I get just minus Rs over r. Period. Nothing else. Nothing else. Yeah? And I think then everything is fine. That's exactly what I wanted to get. Okay, so this is the so-called time-dependent Wheeler equation. So it's a partial differential equation for a function of t and r or if you like this better, t and r star. Yeah, that's up to you if you want to view it as a function of t and r or as a function of t and r star. The two things are related by this one-to-one relation. Well, usually one uses r star. Okay, before I discuss this, in particular before I plot the potential, which depends on L. Yeah, you see the potential depends on L, but not on M. This, of course, means that also the solution, QLM, will not involve the M. Yeah? If the differential equation doesn't involve the M, so why and how should the solution depend on M? It doesn't depend on M. So actually what we have called QLM is independent of M. Yeah? So if I have here the same L and here different M's, M always runs from minus L to L, just to remind you, then I get the same number. So differential equation, that's a German abbreviation. Okay, let me write differential equation independent of M. And this means we can reduce QLM, we can replace QLM just by QL. Yeah, we don't need the M anymore. Well, if you have done this a couple of times, you know this without doing it every time again. Whenever you have a spherically symmetric problem and you do this kind of separation, expansion with respect to spherical harmonics, then always the coefficients depend only on L, not on M. Because, well, what does this mean? It means that you can choose your axis with respect to which you develop your, you expand your function with respect to spherical harmonics. You can choose any axis you like, right? So the L is really if you think of the Schrödinger equation for, I don't know, Coulomb problem or something like that, hydrogen atom, then of course the shape of the orbital, which is given in terms of the L, this of course does depend on L. It's different for different L's. But you can rotate the axis as you like, and this means there's no dependence on M. So actually, in hindsight, we could say that we should have expected this, and we could have dropped the index M on the Q and also on these V's. Yeah, the Q was just a substitution for VRLM, so this is also only a VRL. So this means that VALM is replaced by VAL. We drop the index M. Okay, now comes the last step. And then when I've done the last step, then I will discuss the equation. So the last step, this is step 6 now, is that we separate off the time. Yeah, we still have a partial differential equation. It's a differential equation for a function of a radius coordinate and a time coordinate. And we can make it into an ordinary differential equation for the radial function by splitting off the time factor. And because the whole system, the Schwarzschild background space-time is independent of t, there's a standard way of doing this. You do it with an exponential function. Yeah, it always works. So we separate, is this a spelling? Or with an A? With A, right? Separate off the time coordinate. So I assume that my function QL is of the form which is a function of t and r, or t and r star, that it is of the form ZL, which is a function of r only, times e to the minus I omega t. Yeah? So I make this separation ansatz, plug this into the differential equation, and then I see what we get. So then we get 0 is, well, second derivative with respect to r star. This derivative acts only on the z. So I get minus, it's now an ordinary derivative, because z depends only on r star. R star e to the minus I omega t. If I differentiate twice with respect to t, I get minus times minus is plus, I times I is minus 1, omega squared. Minus omega squared, there was a c squared. C squared ZL e to the minus I omega t. and then the retro-Wheeler potential. Yeah, so I said that the whole thing is called the retro-Wheeler equation, and this potential is usually called the retro-Wheeler potential. QLM is ZL times e to the minus I omega t, and everything is 0. And you see, as I said, this ansatz works, so the time factor drops out, which is always the case if you have a time-independent problem. Okay, now we have an ordinary differential equation for this radial function. And you look, well, maybe I should, I write this term to the other side, then it's even more obvious that this should remind you of something, this equation. So this is this term with a minus sign, then I have plus the potential term, star ZL R star, and this comes to the other side with a plus sign, omega squared times Z. So this is what is called the time-independent retro-Wheeler equation. Or if one just says retro-Wheeler equation, one usually means this. So I put this in bracket, retro-Wheeler equation. So it's an ordinary differential equation for the radial function. And this looks very, very similar to the Schrödinger equation. Yeah? Kinetic energy operator, well, in quantum mechanics you have an h bar squared, yeah, because the dimensions are different. The potential has a different dimension. But let's forget about the h bar squared. And this is just potential as a kinetic energy, as you know it from quantum mechanics. This is a potential energy, yeah, and this is the eigenvalue. Yeah, it looks like an eigenvalue equation for the ZL, and this is the corresponding eigenvalue. In quantum mechanics, it's the energy, which is h bar times omega. Here we have an omega squared. Why do we have an omega squared? Because our differential equation is second order in time. Yeah? Schrödinger equation is first order in time. That's why we get an omega squared. But apart from this, it's very similar. And actually, many techniques which you learn in quantum mechanics in order to solve this type of equation carry over. And you do this here for the retro-Wheeler equation. But there are also important differences. The first important difference is that here our radius coordinate runs not from 0 to infinity, as a radius coordinate in the ordinary, for the ordinary spherical polar coordinates does, but rather from minus infinity to plus infinity. Yeah? That's the first difference. Second difference is, just as in quantum mechanics, this is a complex function. Also, the ZL is complex. Why are all these functions complex? Maybe I should have said this. Not sure if I've ever mentioned this. Because we make an expansion with respect to spherical harmonics. Here we still have it. And these things are complex. Yeah? Remember, they have this factor e to the I m phi. So they are complex functions. This, of course, is supposed to be real. We want to have a real metric perturbation. But if you expand this with respect to a complex basis, you get complex coefficients. Yeah? So our coefficients are really complex. But they must be, they are not completely arbitrary. Yeah? So the relation between imaginary and real part is not arbitrary. They must combine to an h mu nu, which is real. So that's different. This condition also has no analog in quantum mechanics, in the Schrödinger theory. Then there is an important thing, very important thing. I said this looks like an eigenvalue equation. In order to, for this statement to make sense, I would have to specify boundary conditions. Yeah? Eigenvalue equations are something which refer not just to a differential equation, they refer to a differential operator on a certain function space. I have to specify the function space. And in quantum mechanics, of course, this is the L2 space. We have the space of square integrable functions. Here, in this context, there's no reason to require our functions to be square integrable, because there's nothing like probability interpretation or something like that, which we have in quantum mechanics. Yeah? So here I have to discuss the boundary conditions I want to impose separately. I cannot just carry them over from quantum mechanics. I think that these are the important differences. And of course, there's another one. This ZL is not the function we are actually interested in. Out of this ZL, we construct the h mu nu, which we are interested in a rather complicated way. And maybe I should now go backward, equation by equation, to remind you how from out of this ZL we construct the metric perturbation. Yeah, because this is maybe not quite obvious, and you might have forgotten it. Oops, maybe I should leave this here. I should leave this here. So I just erase the right-hand portion of the board. And then we will discuss what kind of solution this equation admits. So it's a second order ordinary differential equation, linear. Yeah, it's linear in ZL. So we know the general solution if we have two linearly independent solutions. And what I write down now is how out of these solutions to the Recco-Wheeler equation we actually construct our metric perturbation, reconstruct I should say. You can do the entire story also for even perturbations. I said already that then it's considerably more complicated, but in the end you get an equation which is very similar. Actually, it has precisely the same form, just with a different potential. Yeah, the potential looks different. It depends in a more complicated way on the index L in particular, but the general structure is the same. And this equation for the even mode, this is called the Cyrilli equation, after the gentleman who derived it first. But I will not treat the Cyrilli equation here. But actually the full set of all perturbations you can consider is of course a superposition of odd and even perturbations. So in general you will also have the even ones. Okay, from a solution QL, we reconstruct the perturbation H mu nu in the following way. So first, the Q was, I just erased this, right? I always erase the equation which I need. The QLM was, the first step was, from the ZL. I already began with a penultimate step. So the last step was, here's this equation. So first, if I have the ZL, if I have a solution ZL, then I get QL as ZL e to the minus I omega t, right? From the QL, I get the VRL, and I have to recall how this was done. This was the substitution we have used. This was R divided by 1 minus RS over RQL. Yeah, we had substituted the Q in this way that this equation holds. So we have now reconstructed our VRL. This is one set of coefficients we need. Yeah, it's independent of L. We have dropped the of M. We have dropped the M. So we need the VRL and the VTL. And so how do I get the VTL? Well, the VTL I get from the equation F3 prime, which I also have erased, I'm afraid. Oh, I forgot to mention, we also had an equation F1, right, which I haven't written again. F1 is identically satisfied if F2 and F3 are satisfied. Yeah, you can check this. At first sight, they look independent, but if you solve F2 and F3 in the way we have done this, and then reintroduce this into F1, you see that it's identically satisfied. So it gives no additional assumptions. So from F3 prime, we get a derivative of VTL. So this was dt VTL was c squared 1 minus RSR QLM. Yeah, we have dropped the L, plus c squared RS over R dr QL. And we have now a time dependence which is periodic, so we will assume that also our VTL depends on time via an exponential function, factor e to the minus I omega t. So I call the prefactor, which depends on R only, I call it capital U, L. And then this gives me an algebraic condition for U. So if I insert this expression into this differential equation, then I get, if I differentiate with respect to t, I get minus I omega UL e to the minus I omega t is c squared 1 minus RSR UL e to the minus I omega t plus c squared 1 minus RSR. And the R derivative is, the R derivative of QL. The R derivative of QL is, yeah, we have Q already. I leave it in this way. Yeah, we have constructed the QL in this way. We know what QL is. So you see, no, I have to introduce this expression. So this is d by dr star of ZL times e to the minus I omega t. Why do I have to introduce this expression? Because otherwise the exponential function wouldn't drop out. And now you see, this gives me an algebraic condition for the UL. It determines UL algebraically. Yeah? So if I determine UL from this equation, this I found. I've solved my differential equation, so I know the ZL. Then this gives me UL. This expression gives me the VTL. So I have the VTL. I already had the VRL. So I have my perturbation h mu nu. And now I have to impose the condition that the h mu nu's should be real. Yeah? So this restricts my possible solutions. Okay, so this is the way in which, okay, let me write the last step. Insert VRL and VTL into this expression here, h mu nu dx nu is VAL phi L m sigma. These things do depend on m, right? These things do depend on m, so I have to fix L and m in order to fix such a basis element, but the coefficients which occur are actually the same for all m's, yeah, as long as L is the same. So dxa, dx sigma, that's it. Yeah, so in this way we can reconstruct from a solution of the Recce-Wheeler equation our metric perturbations. So we do this for a fixed Lm, yeah? And actually we have to do it for all Lm, and for the reason I explained in the beginning, we only consider the case that L is bigger or equal than 2. And now comes the important question, can I superimpose these solutions? Actually, I'm interested in a solution which is not just, which has not just a fixed L and a fixed M, but it's rather, it's an expansion with respect to these spherical harmonics. So I want to have a general solution. So I want to consider sums of such terms. And when I came across this derivation for the first time, I got stuck at this point, and I thought, hey, wait a minute. We have introduced a gauge. Yeah, a gauge means we have made a coordinate transformation. And this coordinate transformation depended on L and M, if you remember. Yeah? And can I superimpose two different solutions for different LMs? Is this meaningful? Or is it not true that I use different coordinates for different solutions? Yeah? And then, of course, I cannot just add them together. But the reason which I overlooked at this stage when I had this thought is that the H mu, of course, depends on the coordinates. Yeah? So if I make a coordinate transformation, then the d-axis transform, and here also the argument transform. So we have now made a gauge transformation. This means these are no longer our background Schwarzschild coordinates, t, r, theta, and phi. These are rather changed coordinates, changed by a gauge transformation. But the h mu is of first order. Yeah? If I multiply this with these terms, then only the zeroth order of these terms matter. And also in the argument, only the zeroth order matters. And the zeroth order is the unperturbed background coordinates of Schwarzschild. Yeah? So here, the x and the dx refers to the background Schwarzschild coordinates. I don't have to transform them. Yeah? If I do transform them, I get terms of second and higher order, which I neglect. And for this reason, I am allowed to superimpose the solutions. So everything is all right. So this gauge, I'm not sure if I mentioned this gauge which we have introduced is called the Recce-Wheeler gauge. And the Recce-Wheeler gauge is indeed a gauge where we can express every perturbation in terms of the background Schwarzschild coordinates as long as we stick to the first order theory. Yeah, but which was our plan from the very beginning. So everything is fine. Everything fits together. Okay, so we have now finished the entire scheme. Everything has boiled down to solving the Recce-Wheeler equation. Yeah. When we are able to solve this equation, this ordinary differential equation, then we have full control of all odd perturbations of the Schwarzschild spacetime for index L bigger or equal than 2. Yeah? And we will discuss this now. So the first thing we have to discuss is the potential. Maybe it's a good idea to plot it. The potential depends on L, on the angular momentum. If you plot this, so you have here R star. The horizon is to the left and infinity is to the right. And if I plot VL of R star, then actually we will discuss this potential a little bit on the next worksheet. But I just show you the plot. It's something like that for different L's. Oops. So it's like that. Oh no, wait a minute, the maximum is shifted to the left, I think. It's in the other direction. Oops. For L equal 2, right? For spin 2. No, it was correct. It was correct, sorry. Okay, it was correct. So this here is L equal 2. Yeah, that's the lowest order for which our derivation is valid. This here is L equal 1. And this here is L equal 2, L equal 3 and L equal 4, of course. So the higher the angular momentum quantum number, if I'm allowed to call it this way, the higher this potential. Well, first of all, it's a barrier, a potential barrier, yeah? Not a well. There are no minima. Yeah? It's a barrier which already indicates that there will be no bound states. Yeah? For bound states, you need something like a well, where a system can settle into. So here you can consider only scattering problems. Something comes in from one side, is partly reflected, partly transmitted. So you can consider scattering problems or problems where things decay. Yeah, if you set a perturbation at some place, then it will die down in the course of time. Yeah, it will partly go to infinity, partly to the horizon. But it's fairly obvious that there will be no bound states. We will discuss this in a minute. And this potential barrier, which is an obstacle for scattering problems, if something comes in, say from infinity, then the more will go to the horizon, the smaller the number L is. Yeah? With increasing L, the potential barrier becomes bigger and bigger, so it will become more and more difficult for the particles to overcome the potential barrier. Well, that's fairly easily understood. If you have high angular momentum quantum numbers, this means you have high centrifugal forces. And high centrifugal forces, of course, this is sometimes called a centrifugal barrier. Yeah, this increase with the quantum number L, This is just an effect that if you have high angular momentum, that then it's more difficult to get through towards the center, or in this case towards the horizon. So that's how the potential looks like. As I said, we will discuss it in the worksheet. We will in particular see, well, I think my drawing is clear enough, so it should indicate that the V goes to 0 for R star to minus infinity and for R star to plus infinity. And actually it goes exponentially. That's what we will prove in the worksheet. So here we will have something which is proportional to e to the R star over the Schwarzschild radius. Yeah. So if R star goes to minus infinity, then this goes to 0. Here it falls exponentially down. And here in the other direction, the fall off is not so strong. Here it is proportional to 1 over R star squared. So towards the horizon it's exponential, towards infinity it goes with 1 over R star squared. We will show this in the worksheet. The essential thing is that it goes down to 0 in both cases. This means if you are either very far away from the black hole or very close to the horizon, then you have a situation where the potential plays no big role. Yeah, where the potential is very close to 0. It has almost no effect. And this means that we can write down asymptotic solutions for the Rätsche-Wheeler equation for R star to plus infinity and for R star to minus infinity. Actually, if you want to solve it exactly, then this, it can be done, but it leads to a somewhat complicated kind of function. So this differential equation which we have here, if you write this out, then you will see that it's a particular case of what is called a confluent Hoyne equation. Yeah? Karl Hoyne was a German mathematician who discussed a certain class of linear differential equations of second order, which now carry his name. And this is a special case of this Hoyne equation. So the Hoyne equation, the general Hoyne equation, has 4 singularities. Yeah, so it has 4 points on the real line where the coefficients of the differential equations become infinite. Yeah? And the confluent Hoyne equation is the equation where 2 of these singularities come together. And this is a confluent Hoyne equation, what we have here. You have to transform the variable. Yeah, you cannot read it immediately. It doesn't look like a Hoyne equation if you just look at the equation. You have to make a certain substitution. Then you can take it into the standard form of a Hoyne equation. And this means that you can write the solution, the general solution, yeah, which is given by specifying 2 basis functions which solve this equation. You can write this in terms of the so-called confluent Hoyne function. So the solution can be expressed in terms of a function which is often denoted in this way, Hoyne C. Yeah, the C stands for confluent. And so for instance, if you use Maple, then you will find these functions under this abbreviation implemented into Maple. Yeah? They are not implemented into Mathematica, but you can easily write a little program where you can also handle these functions in Mathematica. Actually, if you want to use Maple, you have to use very peculiar conventions which Maple is using. So in a sense, it's maybe even an advantage if you write the program yourself, for instance, in Mathematica, because then you can use your own conventions. But so these functions are defined, or at least one way of defining them is that you write down a series, an infinite power series, which converges on a certain interval, not on the full interval, only on a certain subinterval of what you are interested in. And this function, Hoyne C, is then the analytic extension of this onto the whole domain you're interested in. So you cannot express this in terms of elementary functions, polynomials or sine or cosine or something like that. It's a new type of function, which can, like the sine function. The sine function can also be defined in terms of a series, right? Also, this can be defined in terms of a series, but the disadvantage is that it converges only on a comparatively small set, and you have to extend it analytically. So, yeah, if you play a little bit around with these so-called ONC functions, then you get control on the general solution. But it's a little bit awkward, so it's not a very elementary function you are familiar with. So for this reason, it is often there are often approximation techniques used in order to solve the Radja-Wheeler equation. So the general solution is given in terms of the exact solution is given in terms of these rather complicated functions, but there are a lot of approximation techniques. For instance, JWKB approximation, or use other potentials which approximate this potential. And the literature is here is thick with approximation methods for this type of differential equation. And a little bit of this I want to do now. What I want to do now is I want to study the asymptotics a little bit. Yeah, the behavior of the solutions if I approach either infinity or the horizon. And then we will draw a couple of conclusions from this. So this is the rest I want to do today. So the observation which I have already indicated in this picture, and which we will discuss in the next worksheet in more detail, is that the potential dies down for r star to minus infinity and for r star equal plus infinity, which means that in this region, very far away from the center, we can actually use approximate solutions of a very simple differential equation, namely where the potential is set equal to 0. So because of this fall-off, the solution of the equation with potential equals 0 is a good approximation for the region far away from the black hole and very close to the horizon. And this is a very simple differential equation. It's just the oscillator equation. And of course, everybody knows how to solve them. And this gives us asymptotic solutions for the exact Radja-Wheeler equation. Sure.
So you said that this is a potential barrier.
Yes.
Right? But for what? For the gravitational waves or for the particle?
For gravitational waves,
okay.
Yes. What we are discussing here, what is coded in this h mu nu, which I have just erased, is a gravitational wave.
So a gravitational wave can have like angular momentum. So it also can be described.
Yes, yes. So what have you been doing in the last two lectures or so? We considered Schwarzschild spacetime and perturbations of the Schwarzschild spacetime which still satisfy the vacuum field equation. And if we exclude these two rather trivial cases that I just change the mass and that I introduce a spin for the center, then what is left is actually these are all radiative degrees of freedom. So these are gravitational waves traveling on the Schwarzschild background. Yeah. And you see, we will discuss this in terms of these asymptotic solutions in a minute. So you can have something which a gravitational wave which comes in from infinity. Part of it penetrates through the barrier, and part of it is reflected. Yeah. That's exactly what we want to discuss now. So for r star to plus or to minus infinity, we have VL of r star goes to 0. Actually, you can discuss how strongly it goes to 0. And so we can discuss, when we neglect this term, we can actually estimate the error which we make. And we will do this in the worksheet. We have VLR, hence minus d2 dr star square ZL. It sets the potential equal to 0. So I have this omega squared c squared ZL. Yeah, as a good approximation if I'm far away. And of course, this differential equation is easily solved. So we have we have solutions, asymptotic solutions. So these are approximate solutions, of course, for the things we have in mind, solutions for ZL. For ZL are e to the I omega r star divided by c with a plus and a minus, right? These are the two basis solutions. So if omega is real, this is just a harmonic wave, right? We have this e to the minus I omega t factor, and if now the ZL, which is in front of this factor, is also of this form, then I get a plane. Yeah, it's one-dimensional in the r direction, so plane was the wrong word, but it's a harmonic wave. Yeah, it's a harmonic wave. So we have asymptotic solutions, asymptotics of two sets of basis solutions. Yeah, it's a second order linear differential equation. So two linearly independent solutions give a basis for the set of all solutions. And if we do this, if we consider this asymptotic near the horizon, then we get two basis solutions. And if we do it at infinity, we also get two basis solutions. Unfortunately, they are different. Yeah? So they cannot be directly identified with each other, and this makes the whole business a little bit difficult. So the things at the horizon are called the in mode and the out mode. And they are defined in the following way. So that LE, the I stands for in. So this is, I write it with this sign. This means it's approximate for big R star, no, for small negative. So for R star to minus infinity. So this is the in mode goes with minus E omega R star divided by C. So this is for R star to minus infinity. Yeah, so this notation means if I write this sign and then write 4 R star to minus infinity, this means if I take the difference of these two things, then this goes to 0 if I take this limit. Yeah, that's what it means. And the out mode is L out, the same thing with the plus omega RSC. So these are two solutions. Of course, you could write them down exactly in terms of the Hohenn-C function, but I will not do this. Yeah? And what I've written here is only the asymptotic behavior. So if in this limit they behave like these expressions. So what is the in mode? The in mode is something which comes here, which comes from the, no, it's the other way around, sorry. The in mode is going towards the horizon, right? The in mode is going towards the horizon.
There should be a star there, right? In the X mode.
Yeah, this is this star. And the out mode is something which comes out of the horizon. If we have a black hole, there shouldn't come something out of the horizon, right? So if you introduce what is usually called causal boundary conditions, then you say that this should be 0. There should nothing come out of the horizon. If you have a black hole, yeah, if you have a white hole, it's the other way around. Yeah, then you would say it's not allowed that something goes in the white hole. But we don't really believe in the existence of white holes. So we are more interested in black holes, and then the out mode should be considered as an unphysical mode.
Can't it be Hawking radiation?
Yes, okay, you know the story. It's exactly what you need for the Hawking radiation. Yeah, so if you extend, you can, with a certain trick, you can also this mode analytically extend to the interior of the black hole. You have to make this into a complex variable. Yeah, the R star is not allowed to go, or if you extend it through the horizon, then you have to go back to the original R. So the original R goes through RS. Then, you have a singularity in your equations. If you have a black hole extension and you want to go with the out mode through the horizon, it doesn't work. But you can make a detour through the complex plane. And with this extension, so we can extend it towards the negative or the r-axis on the other side of the horizon if you make this detour. And with this complex extension, this complex analytic extension, you can explain Hawking radiation. That's one way in which you can explain Hawking radiation. This was an observation. It was not the way Hawking himself introduced the Hawking radiation. It was a way in which Damour and Ruffini explained the Hawking radiation. But I will not discuss Hawking radiation here.
But Hawking radiation is like a particle radiation, right?
Yes, actually you can do it with any spin. Yeah, you can consider Hawking radiation for any spin, and this would be a Hawking radiation with spin 2 fields. Yeah, the h mu nu, we interpret it as a gravitational field, as a gravitational perturbation, but you can interpret it as any spin 2 field.
So it's like gravitational radiation.
Yes, yes, yeah. So maybe I should have said that this is what Recce-Wheeler originally did. It was exactly this equation they derived. But now the word Recce-Wheeler equation is considered in a more general sense. You can consider not only spin 2 fields, as we did here, in particle language. Yeah, this h mu nu with 2 indices. You could also do it for scalar fields, for vector fields, and if you like, also for higher order spin fields. The only difference is that you get different factors here. Yeah? So for spin 0, you get instead of -3, you get a +1. For spin 1, you get a 0. That's a particularly simple case. And for higher spins, you get higher negative terms. And all these equations are usually called Recce-Wheeler equations for a certain spin, although they don't occur in the original paper by Recce and Wheeler. So, what we just discussed in connection with Hawking radiation can be done with any spin. Yeah? And actually, there's no difference. Also, with respect to the temperature and what else you derive for the Hawking radiation, it's the same for all spins. Okay, but I don't want to talk about Hawking radiation here. I want to talk about the quasi-normal modes and a little bit about the scattering states. Okay, this is one basis. Yeah, this uses the asymptotics near the horizon. But you could also use the asymptotics at infinity. Then you get what is called the down mode and the up mode. So this is ZL down is again proportional to this expression, but now for R star to plus infinity. Yeah. Also there, the potential goes to 0, so I could use this approximation, e to the plus omega R star over C for R to plus infinity. And now you might be tempted to suspect that actually this is the same as this here, yeah, and this is the same as this here, but this is not true, yeah. So these things, either of these two functions, is a linear combination of both of them, yeah, and this is what makes the story a little bit more complicated. So you can have here the up mode. This is this here, which goes away from the center, and you have here the down mode. So for instance, if you have causal boundary condition, if you say you have no out mode, then you have, at infinity, you have an up mode and a down mode. Yeah? So this is a typical situation when you have a scattering problem. Something comes in, here that's the down mode. Part of it is reflected, that's the up mode. Part of it goes to the center, that's the in mode. Yeah? So one of them, actually each of the four is a linear combination of any of the other two. Yeah, you can also use mixed spaces. You could use these two as basis elements, or these two. So these are the possibilities. And you see, when omega is real, I haven't said this clearly, and actually all the derivations I've done, all the calculations I've done, work equally well for complex omega. Yeah, but if omega is real, then this is just, as the name suggests, a wave-like solution which goes inward. This is a wave-like solution which goes outward, and analogously for these things. If the omega has an imaginary part, then there's also something which is also a factor which introduces either an exponential damping or an exponential growth. Yeah? If this has an imaginary part, then the two i's kill each other, and then you have something real in the exponent. This is either going up or going down exponentially. So what does this mean? Well, Because if you want to have a real omega means for our time factor, e to the minus I omega t, it means that this is just an oscillation. Yeah, with real omega, this is just, if you decompose it into a real and imaginary part, it's a cosine and a sine function. So it's something which goes sinusoidal. And the amplitude is independent of t. So this is what one would call a stationary solution. Yeah? So it's something where, okay, it oscillates, but it oscillates with an amplitude which is time independent. And there's no damping term. And now from the existence of these basis vectors, you can easily realize, what is obvious from the picture also, that there are no bound states. What would you call a bound state? A bound state would be something which is oscillatory. This means with real omega, and it would fall off to infinity and to the horizon. Yeah? And would just sit there, oscillate there, but it would not decay. Yeah, that's what you would call a stationary state. But try to form a linear combination either of these two or of these two, which goes to zero at infinity or at the horizon. It doesn't work. Yeah? It simply is impossible. So any linear combination of these two things is actually oscillatory with respect to the R star, if omega is real. And there's no decay for omega real. So the only way in which you can construct something which goes to zero for infinity or at the horizon is that both coefficients are zero. Yeah? So you have a linear combination of these two things, and they fall off for infinity only if both coefficients are zero, and they fall off towards the horizon only if here the two coefficients are zero. This means the function is identically zero. Of course, this is kind of a stationary solution, but that's not what we're interested in. So there are no stationary solutions. So from this observation, we observe from the existence of these basis vectors, we see that solutions with real omega cannot non-trivial, as a non-zero, I mean non-trivial solutions with real omega cannot go to zero for R star to plus or minus infinity. Not even for one of the two limits, let alone for both. And this means, of course, that there are no, in quantum mechanical language, one would say bound states, or in the theory of oscillations, one would call this normal modes. Yeah. So there are no normal modes, but there are what is called quasi-normal modes. What's a quasi-normal mode? A quasi-normal mode is something of this form, but where the omega also have an imaginary part. Yeah? What does an imaginary part mean? It means that the thing goes either up in the course of time or down exponentially. Of course, we are not interested in something which goes up to infinity. This would be something which would look unphysical. Yeah? If in the course of time the thing becomes bigger and bigger, we are in a theory where our h mu nu is a small perturbation. We have linearized with respect to h mu nu. This should better not grow to infinity. So then the whole theory would be rather nonsensical. And so but we could consider things which die down. This is a very reasonable physical assumption, and these solutions exist, and they are called quasi-normal modes. And where they could be studied in terms of these Hoyne functions, and but long before this relation to the Hoyne function was discovered, actually the quasi-normal modes have been calculated, and this was done numerically. Yeah, so the quasi-normal modes have been calculated numerically, and I just show you the results. But there exist quasi-normal modes. This means solutions with complex omega So omega is something like an omega r, which is a frequency, as we are used to frequencies. And then comes an imaginary part, which is a damping constant. Yeah? If it is, well, what are our signs? The term goes with e to the minus I omega t. That's my convention. Some other authors use a plus here. Yeah? It's purely conventional. But I've chosen the minus, which is actually the majority convention. And then, the imaginary part of omega should better be negative. Then it would go down, right? So I have one minus sign. I times I gives another minus sign. So I get a plus, but I want to have a minus sign. It should fall off, so the omega I must be negative. Yeah. So it's complex and omega. Yeah. They describe damped normal modes. So normal modes which in the, they are not normal modes in the strict sense, that's why one calls them quasi-normal modes. But over a certain time interval they may be viewed as something like normal modes, but then they go down in the course of times. And they are really damped if omega I is smaller than 0. Yeah, so we have seen it doesn't work with omega I equal to 0. And now the intriguing question is, are there solutions with omega I positive and omega I negative, or only with one sign? And this was one of the main results of the Reggio-Wheeler paper, that they have shown that there are no modes which grow in the course of time. And this is what is called modal stability of the Schwarzschild black hole. Yeah? So it's a particular way of discussing stability in terms of these modes. Therefore, it's called modal stability. And it could be shown that actually modes with positive imaginary part doesn't exist. And where are these? Where are these quasi-normal modes? Actually, they have a negative imaginary part, so I should.
If we assume that there is a positive part, then we come into a contradiction.
Yes. Well, actually, it's not a matter of assuming something. You have to check if solutions exist with positive or negative imaginary part. And so it's a boundary condition. Do I have a solution with complex or exist quasi? No, of course I must have the right boundary conditions. So with, let's give names to them, quasi-normal modes. So it's, these are ZLs, right? With ZL no, how should I write this? I should write this in terms of these basis vectors with no in mode, no out mode, and no down mode. Yeah, so the thing decays. So of course there will be something falling in, and there will be something going up, yeah, because the thing decays. But nothing should come in from either side. Yeah, so the out mode should be 0 and the down mode should be 0. Otherwise, of course, I could produce whatever I like. Yeah, if I send something into the system, then of course I can produce whatever I like. But the idea is, what happens if I just produce a certain perturbation, localized? I just place it at a certain position, and then I let it go. I just watch it. Yeah. Then it would decay, so it would go out, and it would go up, and it would go down. And the question is, does it really decay, or does it become bigger in the course of time? Yeah. So from the mathematics, it's not obvious that modes with omega I bigger than 0 don't exist, but this was found fairly early numerically. And then with more sophisticated analytic methods, also in a semi-analytical way. And what one found was the following: that there are solutions 1, 2, 3, 4, 5, 6, I need more, 7, 8, and then the axis is reached. The ninth, number 9, is on the axis, and then it goes back again. Infinitely many. Yeah, and then it goes down. So you have one particular mode where the real part is 0. This means the thing doesn't oscillate. Yeah? And the most important result is there are no solutions with positive omega I. So all omega i's are negative. And there's one where the real part is 0. So this is something which just decays without oscillating. All the other ones have oscillating components and this exponentially decaying factor. So this is for L equal 2. This is the lowest, the lowest order for which this calculation works, and it looks similar, at least qualitatively, for higher order L. It's always true for any L that I have just one solution on the axis. Yeah? So it approaches the axis and then it goes down. So this is what you would call, actually this is infinite in this direction. So in a sense, this is a ground state. Yeah? But the ground state is not the one with the smallest omega I, or omega R, but rather with the biggest one. So it's different from the hydrogen atom, right? The hydrogen atom, it goes up. So and then it approaches infinitely the 0 line. So you begin with the ground states and the first excited state, second excited state, and so on. And there are infinitely many coming before the axis is reached. Here you begin at a certain point and then you go down. And then you go down with both with the real part and with the imaginary part.
So we never reach this omega R also with a lower branch?
I'm sorry?
So we never reach omega R also with a lower branch of this?
So you mean if this stops somewhere?
No. I mean, if we reach omega R, you said that this is the maximum value for omega R.
Yes.
So
This is the maximum. Yeah, this is so this goes asymptotically down. So the deeper you go, the more it becomes vertical, and this is actually a smaller value than this value here. Yeah, so it's the biggest value of the omega R. And where the interesting question is, how big is this omega I? You can really calculate it numerically. In the written lecture notes, I will give you a list of the first values of this omega I. And of course, it scales with the mass of the black hole. Yeah, the mass is the only parameter which is in the game, the Schwarzschild radius, which is up to natural constants, just the mass. And the interesting thing is if you insert for the mass, say, a few solar masses, which is true for the so-called stellar black holes, and for the supermassive black holes is even much bigger. Already for the stellar black holes, this is a very, very small value. Yeah, it's in the order of, let me see. Oops. Did I write it down here? With a few solar, okay, I didn't write explicit numbers here in the text, but I wrote for a few solar masses, the frequency is in the order of kilohertz, and the damping time is in the order of milliseconds. Yeah? So this is an inverse time. There's an inverse time. The frequency is 1 over time. And this time, which is in the denominator, that's the damping time, right? So the bigger this thing in the denominator, if you write this as 1 over tau, then the bigger tau, it means the longer it takes until the thing, until this oscillation dies down. And this is for a stellar black hole already, it's in the order of milliseconds. Yeah? So the perturbations die down very, very quickly for big black holes. It's different for the so-called mini black holes, yeah? Which are hypothetical. Nobody has ever seen one. Well, strictly speaking, we also haven't seen stellar or supermassive black holes, but we have good indirect evidence that they exist. The mini black holes are certainly much more speculative. For them, actually, the damping times would be in a different order of magnitude. But for the astrophysically existing things, for the stellar black holes, this is a very small number. the damping time is very small. So if you hit a Schwarzschild black hole with a hammer, then it will become, well, you are not allowed to hit it really hard, yeah? So that you go beyond this linear approximation. You have to stay within this linear approximation. But if the perturbation is small enough so that all the approximations are allowed, then the perturbation will die down very, very quickly. Yeah? So it will become a Schwarzschild black hole again in a very short period of time. So this was the main result of the Reggio-Wheeler paper. Okay, time is out. I think I will say a few words about scattering next time. So when we consider here we have for the quasi-normal modes, we have assumed that nothing comes in. Yeah, nothing comes in and nothing comes out of the horizon. We can consider the scattering problem where we do send something in from infinity. Yeah. So we send a gravitational wave towards the black hole. Part of it will be reflected, part of it will go to the horizon. And the question is it possible that more comes back than I send in? Actually, we say that's a crazy idea, but there are systems where this happens. This phenomenon is called superradiance. And there are actually other black holes, more complicated than Schwarzschild, where this occurs. But I think what I will prove on Monday is that for Schwarzschild, superradiance does not occur. So that in the Schwarzschild case, what comes back, what is scattered backwards towards infinity is always less than what you send in. Yeah? This is not true for the Kerr spacetime, for instance. Yeah? And this gives rise to the famous black hole bomb, maybe some of you have heard about, which was introduced by Tucholsky and Price in the 70s, or early 80s? I think 70s. And which is still discussed. Okay, so I will continue a little bit with this on next Monday, maybe for half an hour or so. And then the rest of the term I will use for exact solutions. So I will definitely do the Brinkmann solutions. And maybe I can also talk a little bit about the Beck Einstein-Rosen solutions, the cylindrical waves. So I have three lectures left, right? Okay, I try to do a little bit on this in the rest. Okay, have a nice weekend.